this problem, it states that a continuous single-effect evaporator concentrates 9,072 kg per hour of a 1.08% salt solution, entering at 311 Kelvin, to a final concentration of 1.58%. The vapor space of the evaporator is at 101.325 kPa, and the steam supplied is saturated at 143.3 kPa. The overall coefficient is equal to 1,704 watts per meter square Kelvin. Calculate the amounts of vapor and liquid product and the heat transfer area required. Assume that since it is dilute, the solution has the same boiling point as water. In order to solve the problem, we must construct first a flow diagram which will indicate the quantities given and unknown quantities. Here shows a flow diagram for a single-effect evaporator. Before solving the problem, it is necessary to make assumptions. For this problem, the assumption is that the evaporator operates at steady state. For us to be able to solve the required quantities, we are going to perform material balance and heat balance calculations. You should always remember that for a steady-state operation, the rate of mass in is equal to the rate of mass out. Thus, the overall material balance for this problem is expressed in the equation F is equal to L plus V, in which F stands for feed, L stands for concentrated liquid, and V stands for vapor. Given the amount of feed, the equation becomes 9,072 is equal to L plus V. For the component material balance, the equation is represented as FXF is equal to LXL, where XF and XL are the weight percentages of the feed and the concentrated liquid, which are 1% and 1.5% respectively. These values, equation 3 then becomes 9,072 times 0.01 is equal to L times 0.015. Simplifying further, we can now obtain the amount of L that is equal to 6,048 kg per hour concentrated liquid. Substituting this value to equation 2, 9,072 is equal to 6,048 plus V. The amount of vapor that is produced for this operation is 3,024 kg per hour vapor. Now that we already know the amount of vapor and concentrated liquid produced, we will use this value in performing a heat balance. We recall that the total heat entering is equal to total heat leaving. Thus, heat in feed plus heat in steam is equal to heat in vapor plus heat in concentrated liquid plus heat in condensed steam. Now, the basic equation for solving the capacity of a single-effect evaporator is expressed as Q is equal to U A delta T, where U is the overall coefficient, A is the heating surface area, and delta T is equal to Ts minus T1. And the heat that is transferred through the heating surface are expressed as Q is equal to S times the latent heat, in which the latent heat is equal to heat in steam minus the heat in condensed steam. Substituting equation 7 to equation 4, we now have FHF plus S times latent heat is equal to LHL plus VHV. The heat capacity of the feed is assumed to be CPF is equal to 4.14 kilojoules per kilogram Kelvin. This is often the assumption for the feeds of inorganic salts in water. Calculating for the enthalpy of the feed, we have HF is equal to CPF times TF minus T1, in which 4.14 times 311 minus 373.2 results to negative 257.508 kilojoules per kilogram. The latent heat of the steam, 143.3 kPa at the saturation temperature 383.2 Kelvin is equal to 2,230 kilojoules per kilogram. Then the latent heat of water at 373.3 Kelvin is equal to 2,257 kilojoules per kilogram. Then, for HL, since the datum is at 373.2 Kelvin, HL is equal to 0. Substituting these values to equation 8, we can now solve for the value of S, in which FHF plus S times latent heat is equal to LHL plus VHV, which 9,057 times negative 257.508 plus S times 2,230 is equal to 6,048 times 0 plus 3,024 times 2,257. This will result to 4,108.20. kilograms steam per hour. Using this value, we can now solve for the heat transfer through the heating surface. Q is equal to S times latent heat, in which 4,108.20 kg per hour times 2,230 kilojoules per kilogram times 1,000 joules divided by 1 kilojoules times 1 hour divided by 3,600 seconds. You may now cancel kilogram, kilojoules, and then the hour, which results to Q is equal to 2,544,801.667 watts. The heat transfer area required can be obtained by using equation 5, which is Q is equal to U times A times delta T, in which delta T is equal to Ts minus T1. Substituting the values we got, we now have 2,544,801 is equal to 1,704 times the area times the change in temperature, which is 383.2 minus 373.2, which leads us to our final answer, in which area is equal to 139.34 meters squared.
So here is an example of crystallization problem where a solution containing 23% by mass of sodium phosphate is cooled from 313 Kelvin to 298 Kelvin in a Swenson-Walker crystallizer to form crystals of trisodium phosphate, the decahydrate. The solubility of sodium phosphate at 298 Kelvin is 15.5 kg per 100 kg of water, and the required product rate of crystal is 0.063 kg per second. The mean heat capacity of the solution is 3.2 kilojoules per kilogram degree Kelvin, and the heat of crystallization is 146.5 kilojoules per kilogram. If cooling water enters and leaves at 288 Kelvin and 293 Kelvin respectively, and the overall coefficient of heat transfer is 140 watts per square meter degree Kelvin, what length of crystallizer is required? So here is a constructive flow diagram in order to fully understand the problem. So in the feed section, we have 23% of sodium phosphate at 313 Kelvin, which enters into a Swenson-Walker crystallizer. And trisodium phosphate to decahydrate crystals are being removed and are converted into saturated solutions, which also be called mother liquor. And the solubility of sodium phosphate here is given, in which it is 15.5 kilogram per 100 kilogram of water. So here are the data given in the problem. So we have here the value of Cp, Qc, the temperature of cooling water that enters and the cooling water that leaves, and the value of U. So we are to calculate here the length of crystallizer that is required. So now let us first solve the yield of crystals produced by the formula for the yield of crystals. So in which R is the ratio of molecular mass of hydrate over the molecular mass of anhydrous salt. So that would be 380 grams per mole of sodium phosphate, the decahydrate, and that's over the 164 grams per mole of sodium phosphate, which is the anhydrous one. Okay, so we now proceed to W1, which is the initial mass of solvent in the feed. So that would be feed minus the 0.23 kilogram of sodium phosphate. Okay, so that would be 1 kilogram minus 0.23 kilogram. So that would be 0.77 kilogram. And that would be the value for our W1. Okay, so again, W1 is the initial mass of the solvent in the feed. So our C1 also here is the initial concentration of the solution. So that would be 0.23 kilogram of sodium phosphate. So that's the mass of our anhydrous salt over the 0.77 kilogram of H2O, which is the mass of our solvent here. Okay, so when we calculate that, that would be 0.30 kilogram of sodium phosphate over kilogram of water. So for our C2 here, which is the final concentration of the solution, so that's 15.5 kilogram of sodium phosphate over the 100 kilogram water. So that would be equal to 0.155 kilogram of sodium phosphate per kilogram of water. Okay, so now we go back to calculating the value of R since we haven't calculated it. So that's 380 gram per mole over 164 gram per mole, and that would equal to 2.32. Alright, so since we now have the computed values, we can now calculate for the value of y. That would be 2.32 times 0.77 times the value of C1 minus C2, which is 0.30 minus 0.155 times 1 minus 0. Okay, so by the way, our E here is equals to 0 since in the first part in our diagram, we assumed here that the evaporation is equals to 0. So that's we are using 0 as the value of our E. So that's over the value of 1 minus C2, which is 0.155 times R minus 1. So our R here is 2.32 minus 1. So if we calculate this, the value would be 0.33 kilogram. Alright, so for the required feed, okay, that would be total feed times the product weight required over the Y. So in our problem, we have a 1 kilogram times 0.063 kilogram per second, and that's over the value of y, which is 0.33 kilogram. So when we calculate that, we will obtain the mass flow rate required in the feed, and that would be 0.193 kilogram per second. Okay, so now let's go ahead and calculate for the initial heat or the Q1. So Q1 here is the heat in the feed, and that would be the mass flow rate required times the specific heat times the temperature in the feed minus the temperature in the liquor. Alright, so substituting all the values, we have the mass flow rate required in the feed, that is 0.193 kilogram per second times the specific heat, which is 3.2 kilojoules per kilogram Kelvin times the temperature in the feed, which is 313 Kelvin minus temperature in the liquor, which is 298 Kelvin. So we have to cancel the K, and also we gotta cancel here the kilogram units. So we are left now with kilojoules per second or 9.3 kilowatts. So that is our Q1. Go ahead and calculate for the heat of crystallization of the required product rate. So our Q2 here is mass flow rate required in product multiplied to the heat of crystallization. So our value here is 0.063 kilogram per second times the QC value, which is 146.5 kilojoules per kilogram. So we cancel the kilogram here and we are left with kilojoules over second or kilowatts. And the value of our Q2 is 9.2 kilowatts. Right, so for the total heat, that would be Q1 plus Q2, and that is equal to 18.5 kilowatts. So assuming this is a countercurrent flow where the cooling water enters at 288 Kelvin and then that water leaves at 293 Kelvin and the hot fluid enters at 298 Kelvin and leaves at 313 Kelvin. So our delta T1 would be here and delta T2 would be here. So in order to calculate for the value of our delta T1, so that's equal to the temperature of heat fluid that enters minus the temperature of cold water that leaves. So that would be 313 Kelvin minus 290 Kelvin. And our delta T1 here would be equal to 20 Kelvin. So in calculating our delta 2, that would be temperature of the hot fluid and minus the temperature of the cooling water that enters. Alright. Alright, so that would be 298 Kelvin minus 288 Kelvin. And our delta T2 here would be equal to 10 Kelvin. Okay, so now we will calculate the LMTD or the log mean temperature difference. So that would be delta Tm. So that's equals to delta T1 minus delta T2 over Ln times delta T1 minus delta T2. So substituting by using all the computed values, that's 20 Kelvin minus 10 Kelvin over 10 times 20 minus 10. So if we calculate this, this would give us a value of 14.4 Kelvin. That's the value of our delta Tm. Alright, so we can now finally calculate for the area required in this problem. So since QA is equals to AU delta Tm, we could get the value of A by dividing Q over delta Tm times U, which is the overall heat coefficient. So we now substitute all the values. The That's 18.5 kilowatts and we convert it to watts. So that would be 1000 watts over kilowatts. Alright. And the value of delta Tm is 14.4 Kelvin times the value of U, which is 140 watts meter squared Kelvin. Okay. So if we calculate this, the area we will be getting would be 9.2 meters squared. And that's it. We now solved the problem. So the length of the crystallizer required is equals to 9.2 meters squared.